Hello class. From last week, that is from our previous lecture, we were able to deduce that if we have a graph, which is the one given on the right pane, if we have a graph and we introduce a small disturbance h in the x direction, then the slope of the curve or the slope of our graph, which is change in y over change in x, is equal to y2 minus y1 all over x2 minus x1. And what is our y2? Our y2 is the point on the y-axis, which is the top one that corresponds to the red dot, and that value is f of x plus h minus what is our y1? Our y1 is the starting point with respect to the y-axis, which is f of x. So we have f of x all over our x2. Our x2 is the x plus h, so we have x plus h minus our x1, the starting point in the x direction, so minus x. So simplifying this, we have change in y over change in x is equal to f of x plus h minus f of x all over, we have x plus h minus x. So x minus x gives us 0. So we have 0 plus h, which is h. And we also saw that taking the limit on our slope gives us the derivative, the differential of the curve. So to find dy dx, what we talked about last week, to find dy dx, which is simply a small change in y affected, or a small change in x, how sensitive will y be if there's a small change in x, which is dy dx. So taking the limit on the slope gives me my dy dx. So this is equal to the limit as that small disturbance that I introduced in the x direction changes to 0 or approaches to 0, f of x plus h minus f of x all over h. Alright, so this is how you find the derivative of a function using what we call the first. So this is known as the first principle. Okay, so the derivative of a function, which is y is equal to f of x, where y is equal to f of x is our graph, is giving us dy dx, and this is equal to the limit as h approaches 0, and that h is that small disturbance which is being introduced in the x direction, f of x plus h minus f of x all over h. And this is known as the first principle of derivative, or the first principle of differentiation. So if you have been asked to find the derivative of a function using the first principle, this is the formula that you quote and find the derivative of that function. Okay, so with that being said, let's look at how to differentiate functions using the first derivative. What we used to generate that formula was y is equal to f of x. So let's see, when we have y is equal to x, what will be our dy dx. Alright, so dy dx is equal to, we are quoting the obvious ones, limit as h approaches 0. Now when y is equal to f of x, the y2 is f of x plus h. Now my y is equal to x. So in response, or in relation to f of x plus h, I have x plus h. Then minus, when y is equal to f of x, I have f of x here. Now my y is equal to f. So instead of writing f of x, what do I put there? X. Very good. So I have x all over that small disturbance h. And this is equal to the limit as h approaches 0, x plus h minus x. So x minus x, that gives us 0, plus h. So we have h over h. H over h, limit as h approaches 0. H over h is what? 1. And the limit of a constant, we have seen previously, that is always that constant. It doesn't matter what the limit is approaching, as long as the function is a constant, the limit of that constant is always equal to the constant. And this 1, we know that any number to the power 0 except 0 is equal to what? 1. So we can rewrite 1 as x to the power 0, because x is the variable. If I raise it to the power 0, I'll get back my 1. Okay, now let's see when my y is equal to x2. Okay, now let's code the formula. dy dx is equal to the limit as h approaches 0, f of x plus h minus f of x all over h. Okay, so dy dx is equal to the limit as h approaches 0. Now I have y is equal to xa. So in relation to the f of x plus h, I have x plus h all squared minus, what is my f of x? So y is equal to f of x. What is my f of x? X squared all over h. Simplifying this is equal to limit as h approaches 0, the square of that, which is x squared plus 2hx plus h squared minus my x squared all over h. This is limit as h approaches 0, x squared minus x squared, that is 0. So we are left with 2hx plus h squared all over h. Alright, now what do we see here? We see that there's a common factor among all these three terms. Alright, we have h here, h there. So what can we do? We can pull it out, or simply put, we can simplify, we can factorize h out of the numerator, h out of the denominator. And if you have a common factor in the numerator as well as in the denominator, you can cancel them out. So factorizing h out of the first term, we are left with 2x plus factorizing h out of h squared is h all over. Factorizing h out of h, we are left with 1. I have h here, h there. I can cross them out. So this is equal to the limit as h approaches 0, 2x plus h. And applying the limit on these terms, we have 2x plus 0, which is equal to 2x. And 2x is the same as 2x to the power 1. Okay, so what have we seen so far? What we've seen is when y is equal to x, dy dx is equal to x to the power 0. When y is equal to x squared, dy dx is equal to 2x to the power 1. So what have we been seeing so far? We've seen that when y is equal to x to the power n, the index in here, over here, is 1. So to find the derivative, multiply the index by the x. So we have 1 times x, which is x, subtract 1 from the index. So we have 1 minus 1 and 0, and that gives us the derivative of y. When y is equal to x squared, dy dx is we multiply the derivative by the x. So we have y is equal to x squared, dy dx is equal to multiply the index by the x. So we have 2x, subtract 1 from the index, 2 minus 1, and this is equal to 2x to the power 1, and that is what we have. So when y is equal to x cubed, then dy dx is equal to multiply the index by the x, which is 3x, subtract 1 from the index. So 3 minus 1, this is equal to 3x squared. Okay, so when y is equal to x to the power n, then dy dx is equal to n times the x to the power n minus 1. And this is known as the power rule. Okay, so let's look at examples. If I have y is equal to 3x to the power 4, then dy dx is the 4 multiplying the function, so 4 times 3x, subtract 1 from the power, so 4 minus 1. And this is 4 times 3, which is 12 times x to the power 3. Okay, so with that being said, let's see if you can solve this. Y is equal to negative 15 x to the power 2. Okay, all right, so it means that dy dx is equal to multiply the 2 by the function, so 2 times negative 15x, subtract 1 from 2, and simplifying this, 2 times negative 15, which is negative 30, x to the power 1. Okay, so now we know that if we have a function, we can use the first principle to find the derivative. We can also use the power rule to find the derivative. Okay, now there are some standardized form of differentiating some functions, and those functions are the exponential functions and then the trigonometric functions. Okay, they have a standardized way of differentiation. That is, it has no alternative way of differentiating such a function. If you have an exponential function, it has only one sure way of finding the derivative, as well as if you have a trigonometry function, there is only one sure way of finding the derivative. If you have a function, an exponential function, which is e to the power f of x, where f of x is a function that is purely in terms of x, then the derivative, that is dy dx, is equal to differentiate the function on top of the e. If you differentiate f of x, we have f prime of x, prime indicating that we have differentiated a function, multiplied by e to the power f of x. So all that you're doing when you're differentiating an exponential function is differentiating the function that can be found on top of the exponential and multiply that derivative by the function itself. An example is if I have y is equal to e to the power x, then dy dx is equal to differentiate x. Okay, so if you differentiate x, what do you get? I have x. It means dy dx is equal to differentiating x, multiply the 1 by the x, so 1 times x, subtract 1 from the 1, and this is equal to 1 times x to the power 0. X to the power 0 is 1. 1 times 1 is 1. Okay, so I have 1 times, multiply the derivative by the function, which is e to the power x. 1 times any number is the same number, so e to the power x. Okay, another example, if I have y is equal to e to the power 2x, then dy dx is equal to differentiate what is on top of the e. If you differentiate 2x, so y is equal to 2x, dy dx is, there's a 1 here, so 1 times the 2x, so 2x, subtract 1 from 1, and this is equal to 2 times x to the power 0. X to the power 0 is 1, so 2 times 1, and this is equal to 2. So I have 2 times e to the power 2x. Another example, if I have y is equal to e to the power x squared plus 3x, dy dx is equal to differentiate what is on top of the function, the exponential function. If you differentiate 2x, multiply the 2 by the x, and we have 2x, subtract 1 from the 2, and you're left with 1. Plus, differentiating this, multiply the 1 by the 3, we have 3 times, subtract 1 from the 1, and you have 0, so times x to the power 0, and this multiplied by the function x squared plus 3x. So simplifying this, we have 2x plus x to the power 0 is 1. 1 times 3 is 3. E to the power x squared plus 3x. And that is how you differentiate exponential function. Okay, now how do you differentiate trigonometric functions? That is, functions of the form y is equal to cos of nx and y is equal to sine of nx, where n is coming from the set of all real numbers, x is our variable, cos and the sine are the trigonometric functions. Now, because we don't have much time, we'll look at what we get when we differentiate either of these two functions or both of these two functions. If you differentiate cos, you get negative sine, okay? If you differentiate sine, you get positive cos. If you differentiate cos, you get negative sine. If you differentiate sine, you get negative cos. Now, because of lack of time, we'll not be proving it. In our subsequent lecture, we'll try and find time to prove these assumptions or theorems or facts. But for now, let's have the idea that when we differentiate a cos, we get a negative sine. When we differentiate sine, we get positive cos. Okay, so how do you differentiate these trigonometry functions? dy dx is equal to differentiate this. First of all, differentiate what you have after the cos, that is after the trigonometric function. When you differentiate nx, n is a number, okay? So what you differentiate is just the x, okay? And the x is to the power 1. So multiply the 1 by the nx, so you get nx, subtract 1 from the 1, and you get 0. Which is x to the power 0. X to the power 0 is what? 1. 1 times n is n. So you have n before differentiating the trigonometric function. And we know that if you differentiate a cos, you get a negative sine. So n times negative sine of nx. Alright? Simplifying this, we have negative n sine of nx. Y is equal to cos of 5x. Okay, then it means the y dx is equal to differentiate a function after the cos. If you differentiate 5x, you get what? 5 times, if you differentiate cos, you get negative sine of 5x. Simplifying this, we have negative 5 sine of 5x. Okay, let's move on to higher powers. Y is equal to cos of 3x squared plus 2x. Then dy dx is equal to differentiate the function after the cos. Differentiating 3x squared, we get 6x plus differentiating 2x, we get 2 times. We know that if you differentiate cos, you get negative sine. So negative sine, it's multiply negative sine of 3x squared plus 2x. Okay, so simplifying, we have the negative multiplying all of these. We have negative out, 6x plus 2, all times sine of 3x squared plus 2x. Okay, another example, y is equal to cos of 6x squared. So dy dx is equal to differentiate the function after the cos. Differentiating this, multiply the 2 by the 6, and we have 12. X, subtract 1 from the 2 and you're left with just 1. If you differentiate cos, you get negative sine, so times negative sine of 6x squared. Simplifying, we have negative 12x sine of 6x squared. So that is how you differentiate the cos. Now if you differentiate the sine, you get positive cos. So if you have y is equal to sine of nx, then the y dx is equal to differentiate what is inside the bracket, or that is what is after the sine. If you differentiate nx, you get n. differentiate sine, you get cos of nx. Okay, so let's look at example. If I have y is equal to sine 5x, then dy dx is equal to differentiate what we have after the sine. If we differentiate 5x, we get 5. Differentiating cos with sine, if you differentiate sine, you get cos of 5x. More examples. Y is equal to sine of x squared. All right, then dy dx is differentiating the function after the sine. So differentiate x squared, you get 2x. If you differentiate sine, you get cos of x squared. All right, and that is how you differentiate exponential functions. That is when y is equal to e to the power fx. Then dy dx is equal to differentiate the function on top of the e, and that gives you f prime of x times the function itself, e to the power f of x. If you have a trigonometric function, that is y is equal to cos of nx, then dy dx is equal to differentiate the function after the cos. If you differentiate nx, you get very good n. If you differentiate cos, you get negative sine, so times negative sine of nx. So if you simplify this, you have negative n sine of nx. And then if you have the other trigonometric function, which is y is equal to sine of nx, then dy dx is equal to differentiate the function after the sine. If you differentiate nx, you get n. If you differentiate sine, you get positive cos, so times cos of nx. All right.